was brought to my attention that some of you attended what can only be described as a party last night. I've reassured the head that the only line breaking that will be allowed going forwards will be by the first 15 rugby team. Is that clear, everyone? Good morning, everyone all right? I'm not really going to I'm not actually Rowan Atkinson, it's fine. It's, yeah. Everyone all right? Yep. I do a roll call. Are any of the line breakers, have any of them made it? Henny, Bueller, yeah. Well, morning, I'm James. So I'm going to start off with a little anecdote because my favourite author is a British science fiction author called Terry Pratchett. Now, hands up who've come across Terry Pratchett. He's a fancy author, excellent. So Terry Pratchett was renowned for turning up at conventions, quite a self-deprecating guy. And he'd turn up in conventions wearing a T-shirt he had made, and that T-shirt had a number of things on it. It said, I think it said, Tolkien's dead, J.K. Rowling said no, Philip Pullman couldn't make it, hi, I'm Terry Pratchett. And ever since the microservices thing kicked off a few years ago, I've been doing some conferences and things, and I thought I'd have my own made. So I've got my own T-shirt as an homage to Terry Pratchett. And what this says is, Turing's dead, Martin Fowler said no, Sam Newman couldn't make it, hi, I'm James Lewis. So you've got me this morning. I think it's right. I think it was the right booking. We'll find out, I guess. A little while ago, a couple of months ago now, still during, in the before times, before we were back face to face, I had an email, which I was really pleased about, from Jacob. This email. It said, "Hi James, how are you?" It was like, "Oh, brilliant, NDC are back in touch. I'll get to kind of come and hang out with everyone again. It'll be excellent. I'll get to talk about technology. I'll get to understand what people are doing, especially in the .NET world. I'll get to see a lot of people writing a lot of code, probably a lot of goats sacrificed on the altar of live demonstrations." I got this email, "Hi, how are you?" And I thought, yeah, I'm fine, Jacob. How are you? "Sam Newman can't make it to NDC Oslo. We're looking for a replacement. Would you be willing to help?" So I think I'm the right booking. It could be that it's one of the others on my T-shirt. I just sent him that straight back, of course. Which, sorry, Jacob. Okay, so what am I going to be talking about today? So NDC is renowned as being a practitioners conference, right? It's renowned as being very hands-on. It's all about code. And I'm still a developer, so I still love that. But I think sometimes it's interesting and useful to chunk up a bit, to think a little bit about some of the higher-level abstractions around how code gets put together, how teams work, how organizations are designed, how the places in which we work, how they work and why they work the way they do. And really that's been my sort of journey over the last, I don't know, what is it, 7 years since we published the work on microservice, Martin Fowler and myself. So this talk is really about that. It's about my journey around microservices and what's happened since. So Martin and I said, we cannot say there's a formal definition of the microservices architectural style. Instead, we went on to list a set of characteristics. And for those of you who were in the great talk about Cupid by Daniel Terse North on, I'm going to say Monday, I wasn't, unfortunately, because I was on at the same time. But Dan was talking about the idea of properties or characteristics as opposed to principles, because characteristics are inclusive, properties are inclusive as opposed to for and against with principles. And we deliberately called out characteristics, things that we were doing, that we were seeing, our teams in ThoughtWorks, which is where I work, and other big organizations, Netflix, the kind of Guardian newspaper, lots of investment banks, lots of folks around the world, the things that they were doing at scale that made them successful. And we tried to pull them all together into one place. You can think of it as a sort of meta-study, really. It's taking all the things that people were doing that were working back in 2012, 2013, and putting them together. And these were the characteristics. Componentization via services, organized around business capabilities, blah, blah, blah. I'm not going to be talking about these in much detail, although I'm going to be talking about what I think are the underlying principles that make these work, or why these have become characteristics associated with distributed systems microservices architecture, which is pretty much the predominant architectural style out there at the moment. For better or worse, I'm sorry, right? It goes on Martin Fowler's website, everyone thinks it's awesome. That's just how this stuff works. So over the last sort of few years, I've been thinking about, are there any underlying properties, any underlying characteristics? And so if you look at a few of these, componentization, but organized around business capabilities, products, not projects, decentralized governance, there's decentralized data management as well. This idea of decentralization, of pushing decision-making down to the people who know the most, and having them make decisions at the point they know the most, not the point they know the least. And decentralizing software itself, decentralizing it into smaller systems that use the fluidity principle. If you saw my talk on Monday morning about Lego, Don Reinhartson talks about the fluidity principle as a core principle for decoupling systems, building things in separate bits in parallel so you can plug them together later on. So these small things that are communicating via a uniform interface generally, and decentralizing them so they're cohesive and decoupled from one another. These seem to be sort of underlying characteristics around microservices. I promised that I'd talk about team topologies, software architecture, and complexity science in this talk. So the first bit is about team topologies. Now, who in the room has read the great book, Team Topologies, Manuel Pais, Matt Skelton? Not that many of you, actually, which is good, because it means the rest of you get to discover it for yourself. So this is a book about, well, really it's another meta-study, if you like, well, I think it is, where the two authors have gathered a whole bunch of information from how, we know that, a whole bunch of information from teams that are building software successfully and put them together into one place and described a common language, a ubiquitous language, in D2D terms, that we can all use to talk about team structures, successful team structures. And what do those team structures look like? Well, they tend to be organized around something called flow. The idea of the flow of stuff, the flow of information, the flow of requirements, the flow of value from, as my old MD used to say, from soup to nuts, from concept to cash, or as Dan says, from concept to the customer saying thank you. So that's what this book is about. It's about organizing our teams so that requirements flow, so that software flows, so that commits flow easily through from idea through into production, where they can make money. But before I get into the types of team they talk about, I'd like to sort of tell you a little story about this symposium I was at. It's an academic thing I was at in the Caribbean. It's a terrible life, going to these things, I tell you. So I was on Anguilla at this little workshop, and there was someone from Amazon there, from AWS in particular, and they said the bigger we get, the easier it becomes to get bigger. The more people we add in AWS, the more teams we bring on board, the easier it is to bring more teams on, the easier it is to build more products. The bigger we get, the easier it becomes to get bigger. And I was kind of a little taken aback by that, right? I mean, that seems to not be how stuff works, in my experience. Who works in a company where, as you bring more people in, it's easier to onboard new people? There's normally one. There you go, one. Do you work for AWS? No, okay, right. Who do you work for? Oh, okay, fine. Yeah, I'm not sure who they are, but... As I said, there's always one. Thank you. Maybe we can talk afterwards. The majority of us work in organizations which follow the general rule. As you add more people, things slow down. As you add more people, the overhead increases, communication overhead increases, things get slower and slower and slower. That is my predominant experience. And I suggest probably the predominant experience of people in the room. So this brings me to this concept of flow. The goal of successful organizational design, in my opinion, is to optimize the flow of value. All else is subordinate to that. We should be looking to design organizations and teams, and therefore software architectures, where the flow of information, the flow of value, is the thing that we're optimizing for. It's the forcing function, if you like. So what is it about AWS? What is it about Amazon that have this organizational design, which means that it's easy for them to add new teams, because that implies the flow of value is faster with AWS. The flow of value is faster with those teams than with bigger organizations where it's harder. Daniel Terhus-North, he has a different way of looking at this. I like this, though. We should be looking as a team to safely and sustainably reduce the lead time to thank you. I like that idea. But what is value? I'll go back. There's someone taking a photo. Pleasure. What is value? So, what do we think of as value in our organizations, on our teams, when we're building software, when we're writing code? Well, I would say value is just stuff, right? Because, what we do, which is about bits, it's about knowledge, it's about information flow, that generates value. We take stuff that's sort of a raw material, someone's idea, a feature request, a business requirements document. They still exist. A business requirements document, and we turn it through through a sausage maker, if you like, successively adding more information to these things until at the end we get something concrete which we can deploy into production, which is, we hope, valuable. It's stuff. But physical and informational knowledge stuff are essentially the same. The systems that we work in, doing knowledge work, are the same as a supply chain optimization problem for a supermarket. That's the flow of stuff from an orange being picked on a tree in Seville through into Tesco's and through, therefore, onto your table. Or a manufacturing process where you get raw materials and you turn it via a set of machines into progressively more complicated widgets. There's a flow of value until you get something that's accrued enough value that it's valuable to be sold. But they're the same thing, essentially. Just one's physical, one's informational or digital. They're the same thing. The flow of value. It's basically taking raw materials, passing it through a network of machines, if you like, or flowing through a system of work and turning it into a thing. Now, I'll give you an example from a retailer I was working at in northern Spain. I have no names, but you might be able to work it out. They could go from a designer, like clothes designer, putting their pencil down, right, on the, they've done their nice design, sketched it all out. They put their pencil down. 15 days later, that design is in shops around the world. Right? You go from pencil down, design, an idea, through into a physical product 15 days later all across the world. They're probably the most highly optimized supply chain in the world. But then when you look at things like the set of DORA reports or the book Accelerate, that's really what that's talking about when we're thinking about things like, like lead times. They talk about lead times, mean time to value, lead time to value. We're talking about how quickly we can go from code through into production. And elite, high-performing teams do that on demand, 15, however many times a day. Low-performing teams, not so much. But that's what we're thinking about in terms of value and flow. And that's what Team Topologies talks about in terms of optimizing team structures and coming up with a ubiquitous language to help us all optimize our team structures for flow. This is an example of how you don't optimize for flow. This is an example of a value stream map, a real one from a client I was at a while ago. And what this shows is, right over this end, still this end if you're over there looking at that one, this end, that's where requirements are captured. This bit here is where they're deployed. There's a tiny little blue post-it up there. I think I might have a laser, maybe not. There's a tiny little blue post-it in there. That's writing code, that is. My favorite bit of this is this bit in the middle, where you've got these circular things. That's two enterprise data architects on different teams who've each got a canonical data model, and they just go around in circle updating each other's canonical data model. One feels that they don't understand what canonical might mean. Doesn't mean what they think it means, clearly. But this is an example of a very old organization that over time have accrued lots and lots of process steps in order to deliver value. Something happened at one point, maybe it was Black Friday and the website went down, they couldn't sell anything, so let's do a 6-week period of integration, regression testing. You get these long value streams, especially in bigger, older organizations. The rest of this talk is about why that is. So back to team topologies. Team topologies describes 4 different types of team. It talks about this idea of a stream-aligned team. This is a team, we talk in microservices land about product teams, right? Product teams organized around value streams, delivering value to a customer. You should have line of sight to a customer. That was one of Jeff Bezos's lines in his famous memo. Each team should have a line of sight to the customer, so stream-aligned teams. You can think of this, maybe a retail website, you might have one value stream or stream-aligned team delivering search, one delivering baskets, say, one doing a catalog page, and so on. You then have enabling teams, complicated subsystem teams and platform teams. The idea behind these other teams is that they make the stream-aligned teams go faster. Why do we want a platform? Why is AWS useful? Because it makes us better, faster at delivering value. That's why we have platform engineering teams, we hope. They can build tools in order to make the other teams go faster or help the other teams go faster. And then enabling teams, this is to manage scarce resources. We all know there aren't enough security engineers to go around. There aren't enough really good, super good infrastructure folks, not enough really good user researchers. So you create enabling teams. You can act as consultants to the other teams, helping them go faster, providing limited skills. So you have these 4 fundamental topologies talked about in the book. And it enables us to have a conversation about how we design our teams around our software. And I'm going to go back to Conway's law here. This is an assumption that everyone knows about Conway's law. Conway's law states that the way your teams are structured dictates how your architecture is going to look. So when I'm talking about teams, I'm talking synonymously with software architecture here. So how we organize our teams is the same as how we organize our sets of domains, our microservices, in business capabilities and so on. Which brings me on to the next topic, software architecture and complexity. Because, designing teams is all very well, designing organizations is all very well, but we're software engineers, software architects probably, some of us. Although I would describe myself as a coding architect, I think architecture is an activity that gets done as opposed to a role. You can have an architect role and not do any architecture, I would argue. But architecture and complexity. Back to what this guy, and there was a guy from Amazon said, AWS, the bigger we get, the easier it gets to get bigger. The more people we add, the easier it is to add more people. The more products we build, the easier it is to build more products. In fact, he went as far as to say, our only limit on the number of products we could be building is the number of people we can hire. Well, that's how quickly we can go at AWS. And if you think about it, what they've built is this sort of foundational platform. So what they're able to do is plonk new teams on. Those teams are able to take advantage of prior art. They're sort of separated from one another. They're just able to sort of plonk these teams on. But as I said, this sort of flies in the face of what we usually think of when we think about certainly software projects. This is the classic quote, adding manpower to a software project makes it later. This is received wisdom. And this was done on the basis of a good piece of research, which showed that as you add more people into a project, there becomes a tipping point where the information, the amount of chatting we have to do, the amount of coordination we have to perform between ourselves overtakes the benefit of the productivity of the new person, or the new people. So there's a natural limit to the size. In fact, microservices was partly a way of sort of, if you like, sidestepping this problem, getting around it by saying, well, if we break stuff up into little bits, then we can have more people working on the little bits, right? That's the idea. Sort of sidestepping around it. My favorite sidestepping of a maths thing story was from a Google talk I was at. I can't remember which database. It's their like massively global, consistent blah, blah, blah database, which has got they bought all the atomic clocks to make it run, right? And at the end of the talk, the Google guy said, yes, I know we're consistent and available in the event of a partition, that should be impossible, right? According to CAP theorem, you can only have 2 out of those 3. He said, the thing is, we're not really, it's just that our networks are so good at Google, we never have network partitions, which I thought was quite entertaining. He's like, we're going to sidestep that by pretending that our networks are perfect, and maybe they are at Google. Anyway, back to AWS. I sort of went home and I ran the numbers as far as I could. I had a look at the amount of money they're making per employee, essentially, at Amazon. I plotted it on a graph based on publicly available data at the time. There's not much of it, so the data science folk in the room, you can pelt me with fruit if you like, but I used what I had, pseudograph coming up. This is log. So what this shows is as Amazon are doubling in size, in terms of the number of employees, they're making more than double the revenue. That exponent, 1.15 up there, forget the rest of it, but the 1.15, that means they're making 15% more revenue than they should, if you like. They're more than doubling the amount of revenue. They're making 1.15 instead of 1. If they were growing exponentially, if revenue growth was exponential with employee count, they would double employees, double revenue. But they're not. They're in advance of that, right? They're doing better than they should. I thought that's interesting and intriguing. Why is that? Is it something to do with the way they're structured, the way their software is architected, the way their teams work? Because clearly, this guy was saying, we can go as fast as possible, or we can go as fast as we can bring on new team members. So I went back again and thought about what happened 10 years ago when they were 15 years, 20 years ago, probably even now, when they moved from monoliths, big monolithic architectures based around databases and database-to-database communication, lots of big Oracle instances and so on, through to where they are today, which is somewhat service-oriented in terms of Amazon.com, and then, with AWS, these small teams building small products disconnected from one another. And all that way back in 2004, one of the things that Jeff Bezos communicated was that from this point on, we must communicate, all teams must communicate via interfaces. There's to be no firtling with each other's databases anymore. CF joke about C and C++ and private. No talking to each other's databases. Everything must be through an API. Everything must be through an interface. Those interfaces must be externalizable. What does that mean? They must be hardened. We must be able to sell them. We must be able to use these as an additional revenue stream if necessary. And we're actually going to manage profit and loss within our own teams. That's what these interfaces and these teams based around these should be doing. And then this famous idea around 2 pizza teams, right? Everyone's come across the famous Amazon 2 pizza team. I've called that Dunbar's number here because that makes more sense. I'll talk about that in a moment. What all these things are, these 3 characteristics, thou shalt do these things, are forcing functions to enable flow. Forcing functions to enable the flow of work within Amazon.com and within AWS. Forcing functions to enable the flow of value as quickly through into production as possible via a set of architectural constraints, if you like, on the software and the teams. So what we're doing is we're limiting interaction to nearby teams. Right, there's a great example at the same symposium I was at. There was someone from Netflix, and they said, well, what we do is we sit people who need to talk to one another close to one another. This is in the before times. Now everyone's a Zoom call away, right? Teams call away if you're unlucky. But we limit interaction to people who are close to us. People I don't need to talk to, they can sit over there. It doesn't really matter. I don't need to speak to the Cassandra admins on a day-to-day basis if I'm working on, the Samsung UX code. Right? But I might need to talk to the platform team or the platform API team because they're the people I need to actually get to make changes for me and things. So I'll sit quite close to them. That way, not only can we have the normal formal conversations, but we might be able to have the sort of serendipitous conversations about work. There's a great piece of work by a guy called Thomas Allen years and years ago now, and he wrote a PhD thesis on. It was a study on research and development organizations or departments. And he looked at how distant you needed to be from other engineers before you stopped talking to them. After about 6, 7 meters, the chances of you accidentally having like a work conversation that was meaningful is 0, pretty much, across the board. After 6, 7 meters, and that includes a staircase, you're not going to have these serendipitous conversations with people, right? So sit people who need to talk to each other close to each other and separate the others. It might sound obvious, but these are forcing functions for flow. Isolate our teams. Use the fluidity principle so we can break these teams up into smaller units which can be linked together, but they're isolated from one another via these interfaces, these externalizable interfaces. And then scale by this well-known factor called Dunbar's number. And if you haven't come across Dunbar's number, it's normally, people talk about the Dunbar's number of about 200, 150, the number of people or connections you hold, the number of colleagues that you could reasonably be expected to know the kids' names of, or whether they like golf, or whether they like swimming or cycling or whatever. Any more than that, you start to lose, they're just people, it just becomes faces in a crowd, if you like. And ThoughtWorks, we'll come to this later, but ThoughtWorks, we used to scale via Dunbar's number. It's slightly different now. But whenever we got an office size over about 200, spin up a new office. Keeps the culture of the office kind of nice and tight. So you scale by Dunbar's number, a number of these Dunbar's numbers. You limit interaction and isolate teams, forcing functions for flow. Fine, James, you've just told me stuff I already know. But this, I think, is the interesting bit, because there's maths that shows why this works. So strap in, calculus coming up. No, not really. It's not. On a Wednesday morning, there's no calculus. There's one more graph, maybe 3 more graphs. So what are complex adaptive systems? So the idea of CAS is complex adaptive system, or complexity science, came out from this place called the Santa Fe Institute in New Mexico. It's no coincidence it's in New Mexico. It's really close to the Los Alamos National Laboratory, which is also there in New Mexico. It's where the Manhattan Project was run. It's where a lot of very famous, very bright physicists worked for many a year. My favorite story about Los Alamos was that on a Friday night, their poker game, just used to have a random poker game, it would have 13 then current Nobel Prize winners playing poker. And that didn't include Murray Gell-Mann, who started the Santa Fe Institute, who went on to win one, or Richard Feynman, who also were playing poker. That's a pretty impressive set of brains there. But a bunch of these folk went off and they got interested in things like chaos theory. They got interested in how these really small interactions can cause, well, chaos, the butterfly effect. Things like Monte Carlo simulation came from Los Alamos. And Murray Gell-Mann in particular was fascinated by the idea of how you get complexity from simplicity. How you go from something as simple as a quark, which he helped discover, to something as complex as a jaguar. And he wrote a book called Quark and the Jaguar about this. How do you go from these indivisible units up to something that thinks and breathes and lives, has its own children? And that's what the study of complexity science is all about. So here's a couple of questions. There might be more than 3 graphs. There's an interesting fact about mice and elephants and humans. Did you know that our blood pressures are all the same? We have the same blood pressure as a blue whale, within bars, or a mouse. We all share the same blood pressure. It is invariant across mammal size. Another thing that's invariant across mammal size is heartbeat per lifetime. You've got a couple of billion, doesn't matter if you're a mouse, you're an elephant, you're a human. There are some invariants across all mammals everywhere. But if you have that kind of thing going on, have these invariants, you probably need some variance too, right? And what varies with mammals is heart rate. One thing, mice's heart beats a lot faster than ours. Elephants' heart beats really, really, really slowly. Blue whales even slower. In fact, what you find if you plot the metabolic rate of mammals with size is a straight line in a graph. This is from the book, well, that's actually from a paper. It's summarized in the book Scale. I'll reference that at the end. But Geoffrey West and James Brown, they found that as you double the size of a mammal, metabolic rate doesn't double. it decreases. That's the variant. Actually, the double the size of a thing, you don't have to eat twice as much. You don't take on twice as many calories. Things slow down. The body slows down. Elephants don't get cancer. You know, that's kind of fascinating because their cells divide so many fewer times than ours do, so they don't get the opportunity to get the genetic kind of problems, you know, building up, defects building up and then causing cancer. They experience the world very, very slowly. We look like we're running around like crazy fools, right? Like mice look to us. Metabolic rate in mammals follows this scaling law with an exponent of 3/4. As a mammal doubles in size, it only needs 75% of the calories. There are other examples of complex adaptive systems. Mammals are one. Organisations are another complex adaptive system. So what about a newsagent, a mom and pop store, and a big supermarket? Well, the interesting thing with these two is if you plot revenue by employee count, you get another straight line. So this is from NASDAQ. And what you find, again, is as you double the size of a company, you don't double the amount of revenue you get. In fact, revenue scales number of employees, blah, with an exponent of 0.85. As you double the size of a company, you only get about 85% of the revenue that you might expect. You might expect to get double, but you don't. You get 85%. Another example of a complex adaptive system is a city or town, right? As you go from one size city and double it to another size, so you go from a village to a town, town to a bigger town, I don't know what the variations in these things are. Bigger town to a city, city to a bigger city, I don't know. What you find is you spend less on infrastructure than you might expect. As you double the size of a city, you only have to spend 85, or I think it's 85%. Yeah, 85% of the money you would expect. You only need 85% of the petrol stations, 85% of the roads, 85% of the sewage pipes, 85% of the light bulbs in streetlights as you double in size. So what we have here is a set of scaling rules that are invariant, that are similar across lots of different things. And the thing they have in common is that they are complex adaptive systems. Geoffrey West, in the book Scale, he says that quantities that do not change when other parameters of the system change, they play a special role in science. And in fact, there's a name for the phenomenon I just showed you. Economists call this economies of scale. This is what our CFOs, we need economies of scale. When you get bigger, we'll get economies of scale. And they're right. You do, for certain things. So linear scaling, or exponential growth, if you like, plotted like this, as one quantity doubles, the other quantity also doubles. But then you have this idea of economies of scale, or sublinear scaling, where as you double one number, the other number increases by less than you'd expect, or less than double. So infrastructure in cities, revenue for organizations, metabolic rate. In mammals, all follow this scaling rule. They all scale sublinearly. Why is that? Well, I'm not going to tell you. You have to go and find out yourself. Thanks very much. I'll be off there. No. I will get onto that in a second. Because it's related to this fact that they're all complex adaptive systems. What are complex adaptive systems? So they have these four characteristics. They display self-similarity. So essentially, a complex adaptive system is anything that can be built from self-similar parts. Right? Our cells are the same as an elephant's cells when you get right down to it. Like a house in one village is the same as a house in another village or in a city as you scale. Self-similar parts. They're self-organizing. Essentially, there's no central conductor that tells the jaguar to build itself. The jaguar sort of turns into a jaguar via self-organization mediated by DNA. They display complexity. So the whole is greater than the sum of the parts. You know, if you sort of atomized a jaguar and then threw all the atoms together again, probably wouldn't get a jaguar. You'd get a bunch of atoms, right? The whole is greater than the sum of the parts. And they display emergent behavior. So the behavior of the whole system can't be predicted from the behavior of the parts of the system. And of course, this is related, if you've come across Dave Snowden's work around Cynefin, this is related to the complex part of the Cynefin model. So all these different complex adaptive systems display these characteristics. And the fascinating thing about the maths now, there's maths that shows that these 4 characteristics can be built from 3 simple mathematical principles, and there is a proof, which I won't go into. But those 3 simple principles are quite interesting, I think. So the first one is this concept of space-filling fractal networks. All the words mean something very specific because maths. Point being, you have these networks. Anything that has a network that looks a bit like this, that is space-filling fractal network, right? That's one of the properties of a complex adaptive system. In us, it's our circulatory systems. It's our nervous systems. Information flowing, blood flowing through those hierarchies, through the networks that we have inside us. The same as an elephant. In an organization, it's the network cables. It's people talking to one another. It's email chains, right? The hierarchies of information flow. These networks that we have. In cities, it's the road networks. It's the water pipes that come in and there's a word for it, split into many small parts before they get into your house, say. You then have this idea of invariant terminating units, which this is what I'm desperately trying to get our staffing people, like folk in ThoughtWorks, to start calling us consultants. Because I think this is way better than, I mean, they normally call us meat bags. I think this is like a step up from meat bags, right? But invariant terminating units, right? People in organizations and like houses in cities, and in mammals, in living creatures, it's cells. Essentially, you know, cells that you get these networks feeding, if you like. And then finally, some mechanism for optimization. Feedback. I gave up smoking 2.5 years ago. It's time for a nicotine replacement thing, sorry about that. It was the best and the worst time to give up smoking, right in the middle of a pandemic, right? It's like, yay, my lungs, boo, I really want a cigarette. But anyway, moving on. Optimization. Optimization, you know, for mammals, that's optimization that's mediated over geological time by evolution. For the other 2 examples, that's market forces, essentially. Whether a city grows or not, or whether a company gets bigger or not, based on feedback from the market forces. And these simple properties, 3 simple properties, they can explain all the lines I showed you. They can explain why you get this complexity emerging from simplicity. At the end of this section, I'm just going to sum up and say, you know, these cases are everywhere. They can be described by these 3 principles: network effects, optimization, and invariant terminating units. When you have hierarchical networks, like our circulatory system, or like the information flow in hierarchical companies, or like the branching and splitting of hierarchies of water pipes, you will always follow this power law with an exponent of less than 1. You can't do better than that. Can't do better than, as you double in size, get as much out, doubling them out that you get out. Generally, what you'll do is you double in size, you get less out than you think, which is good if it's going to cost you money. As you double the size of a company, you only have to spend 85% of money on network cables, but you only get 85% of the revenue. Yeah, fundamentally, this self-similar thing is kind of fun. We are the same as animals, like mice. The Etruscan shrew and us, there's no different mathematically. We're both examples of complex adaptive systems optimized by geological time, by evolution over geological time. So let's come on to this idea of corporate metabolism, because I talked about mammals and how mammals, you know, bigger the animal, the slower they get. But there's also this thing with age. The bigger the older the animal, the slower they get too. Metabolism slows down with age. So why does revenue growth slow as size increase? Why do we get this straight line? Why do metabolic rates slow as size increases? And it's fundamentally down to these interesting networks. Talked about networks, talked about it being one of the first principles, the first principle. The network effects cause metabolic rates to slow down. They cause the effect of not having to spend as much on infrastructure over time. And there's a really interesting reason for this, and it's based on this idea of back pressure and optimization, because systems optimize for the flow of stuff. So for example, if you go from a water pipe, giant water pipe feeding London, there's more than one, I appreciate, right? It splits and splits and splits and splits and splits and splits till you turn on your tap. That's the invariant terminating unit, and the water's all going to flow, right? Same with us. We've got a heart. We've got a big, big pipe called the aorta. And as it splits and splits and splits and splits and splits and splits, it gets down to capillaries, right? Which is they're the width that can feed cells, essentially. Right? If they didn't get down as small as capillaries, then our cells wouldn't get any nutrients. We wouldn't be able to live. The funny thing is about that as well is as you go from arteries, where you can take a pulse, right? You get a pump action from the heart. The capillaries are so narrow that blood flows, there's laminar flow through them, basically, constant flow. There's no pumping mechanism through the capillaries, right? Because if it was pumped, there wouldn't be enough time for the nutrients to skip over the boundary, cells wouldn't get any energy. And the difference between a mouse and us and a blue whale is simply the number of layers of artery that we have. Just counting the number of layers of artery mathematically will give you our metabolic rate. We'll plot us on that graph. That's weird, isn't it? It's very weird, people nodding. It's very, very weird. I don't believe you, James. It's true, there's maths, there's papers. I've referenced them at the end. In fact, the smallest mammal, which is about the size of my thumbnail, the Etruscan shrew, it only has basically the heart and one little artery, then capillaries. But it has to have some form of pumping mechanism to get blood round. Blue whales, they have lots of layers. As you add more layers, things slow down. Blue whales are slower than Etruscan shrews, their metabolic rate, because they've got more depth of hierarchy. That's just maths. Oh, there's another funny thing as well. So in terms of optimization, every time one of like an artery or a water pipe splits, what an engineer would do with the water pipe is make sure they split into pipes with the same cross-sectional area. So the two that it splits into, when you add them together, you get the one above it. And the reason is, if you didn't have that, the water would rebound off the pipe boundary, and it would put back pressure up the system and blow up the water pumping station somewhere. Same with us, with evolution. Evolution is optimized. Every time one of our arteries splits, it splits into two blood vessels with the same total cross-sectional area as it was before. Otherwise, blood would be rebounding off that boundary. You get an impedance mismatch, and basically you put undue pressure on the heart. You get a heart attack. This is why plaque, cholesterol is so bad, because it narrows the arteries. It causes, essentially, the heart to beat against itself. That's kind of... Well, fundamentally, when you look at complex adaptive systems that involve hierarchical networks, these circulatory systems, what you have is these invariant terminating units at the bottom, cells, and then you have layers of hierarchy. And the depth of the hierarchy corresponds to how much more slowly things go. So bigger animals, they're more efficient, if you like, because you only need to eat 75% of the stuff. But because of this, the way the circulatory system has evolved over time, driven by feedback from evolution, they go a lot slower. Bigger companies are more efficient. And they develop deeper and deeper hierarchies, or tend to as they age. I refer you to my value stream map from earlier, from an older organization, really deep, long value stream map, really deep hierarchy through which information is flowing, stuff, value is flowing. You develop these deeper hierarchies. And both of these things, they slow down as they get older. So, flow. I'm going to come back to this value stream map because I think it's interesting. Really, value stream maps, when you look at them, they're just a view through the hierarchy of an organization, right? They're a view of how you get work from one place to the place it's supposed to be delivering value. From requirements capture through into production. They're a slice, if you like, through the corporate information hierarchy. Here's a fun thing you can see in this value stream map. These little arrows are pointing to queues of JIRA tickets, backlogs, requirements sitting there, doing nothing, just hanging around, waiting for someone to pick them up and do something, right? Now, when we look at how flow works from an economic perspective in the principles of product development flow, Don Ronison points out that queues create all sorts of issues. The longer something sits in a queue, a work item, then the more chance that something's going to change and the requirement becomes out of date, say. The deeper the queue, the longer it takes anything to get done. And so what we have with this idea of corporate metabolism is that as companies grow, as they scale, as they get bigger, they add more layers into their corporate hierarchy. They add more process stages to get stuff done. You add more process and more hierarchy. And it's maths. The more hierarchy you add in these networks, the slower you will go. It's just maths. But we also deliberately block our corporate arteries. We do stuff that, personally, I find irritating. I suspect some of these examples you might too. So can we actually identify the signs of aging in our organization and take action, potentially, to speed things up, to get younger, the elixir of life? Can we do that? So in the book Accelerate, which is the summary of the state of DevOps reports over a number of years, they identify 4 key metrics which are the equivalent, if you like, of taking your pulse, your blood pressure, your temperature, leading indicators of corporate health, of corporate metabolism. But before I get to those, here's a fun fact. Who likes change request boards? Wake up, Bueller. No, architecture review boards. Who's got an architecture review board they have to go to? Yeah. So in Accelerate, they find that, and I'm going to use this word precisely, change request boards, architecture review boards, predict low performance. I'm using that in the precise statistical sense. They predict low performance. And if you think about flow, if you think about what I've been talking about, it's kind of obvious really why. Because what we're doing is we're deliberately blocking. It's like we're stopping the blood supply to our arm for a bit by applying a tourniquet and then releasing it. That's essentially what we're doing when we're putting requests into a change request board or an architecture review board. They predict low performance. But we can use the tools from Accelerate to predict, as leading indicators of organizational health. So mean time to recovery, cycle time, they call out, change failure rate, number of deploys. There's a new one added, which I think is availability. I can't remember. And we can use these to test whether we're getting faster or slower and work to improve them. Again, Daniel Turhurst North, he's got this lovely line. We should be working to sustainably and safely reduce the lead time to thank you. And by optimizing around these 4 key metrics, we can do that. So they're leading indicators of org health. It's like monitoring your blood pressure. It's the same, because it's the same network effect that's going on. It's the same thing with flow. But you should remember that any improvement you make is always going to be limited by the depth of hierarchy. Hierarchies mean that we can only get so fast, and we can get no faster. But we can work to reach the limit by optimizing the 4 key metrics. Organizational mortality. So the churn on the half-life of an organization, a listed company, not anyone in particular, so I said half-life, the half-life of a listed company is 10.5 years. Every 10.5 years, there's 50% churn on any, on the NASDAQ, on FTSE, or whatever it is. Companies die all the time. They get taken over, they go bankrupt, they go into administration, et cetera, et cetera. And why is that? Well, it seems as if, over time, organizations, and there's less data available on this, because there's more publicly available data on cities and mammals. But it seems as if, over time, organizations spend less on R&D. They spend less on the thing that made them vital, if you like, to begin with, which was the products they were building for their customers to delight them. They concentrate less on doing that. They invest less of their metabolic energy, if you like, into life, into vitality, into thriving, and more into cell repair, cost efficiencies, moving people around so we don't spend as much money, that kind of stuff. And it means that as these companies get older, they end up dying. You add more and more processes and constraints until eventually everything seizes up. And you've got nowhere to go. Because the hierarchies are growing and growing and growing, adding more and more processes and constraints, spending less on R&D until eventually, like mammals, they cark it. So hierarchical organizations, they gain economies of scale for infrastructure. They achieve sublinear growth in revenue, economies of scale for revenue. And they reduce their metabolic rate over time until they eventually die. Thank you very much. I'm James Lewis. Hope I haven't depressed you all too much. I'm joking. Because there's a way out, everyone, don't worry. But thank you for the applause, that was quite good. I should do that joke more often. You were awake, or at least there was probably someone at the back who went, or maybe all of you did, I don't know. Because there's a way out, right? There's actually a different way. Amazon are doing it, AWS are doing it. Other companies have found a way around this trap. And that's because there's another straight line you can plot on this, which economists call returns to scale. As you double one number, you get more than double out, as opposed to less than double. Cities do both. Cities have economies of scale for infrastructure, and they have returns to scale for socioeconomic factors. So innovation, wages, the number of professionals, the number of camera shops, all sorts of stuff. You get more than double these things when you double the size of a city. And you have less than double of road length, the infrastructure stuff. The infrastructure stuff that is based on hierarchy, right? The hierarchical networks. Incidentally, if you thought that people walk faster in London than elsewhere, they do. MIT did some research. As you double the size of a place, people walk faster. It is actually a thing. They analyze mobile phone data. And that's the number they came up with, obviously, up to the limit of needing exoskeleton legs. And the reason is because there's a different type of network acting with socioeconomic effects. There's something called a small world fractal network. Same mathematical properties, if you like. It's a fractal space-filling network, but it operates, it's not hierarchical. It's like your Twitter friends. It's like Facebook. It's like a social network. It's like your connections with your friends and family. And social networks drive superlinear growth. I mentioned Dunbar's number. There are more than one Dunbar's number. Excuse me. They scale from 5 all the way up to 500. 5 is your nuclear family. It's awkward for me because I've got 4 kids and my wife, so I must love either one of the kids less or my wife less. But then you get 50, your close friends, your nuclear family, if you like, a very close family. Then up to 50, which is probably your cousins and things. 150, your acquaintances. 500, the people you know that they like golf. And returns to scale are driven by these types of networks, social networks. Hierarchies drive economies of scale. Social networks drive returns to scale. And the reason is because some smaller networks, you can grow stuff on the side. You don't need to, I've gone back to comp sci, my data structures and algorithms course, inserting a node into a linked list or into a graph or whatever how you want to be doing. That's probably an interview question I've failed at one of your companies. You don't need to do that, right? With hierarchies, you need to add depth. With smaller networks, you just plug bits in on the side. You add suburbs. Where I live in Stevenage, it's constantly having these little suburbs, little estates added on the side without disrupting the rest of it. And that's why small world networks drive returns to scale, because they're independent, they're decoupled, they're isolated from one another. So as cities grow, they gain economies of scale for infrastructure, but returns to scale for the other stuff. It's not all good. Crime more than doubles. Right? Disease more than doubles. But so does wages, innovation, and so on. They also rarely die. You can actually measure the crinkliness of a city, the boundary. The fractal dimension of a city tells you how healthy it is. And as Detroit sort of became ailing over the last sort of couple of decades, and then sort of sparked back to life a bit, the fractal dimension has increased of Detroit. Actually measure that. I think you could probably do the same with software architectures I've not tried. Fundamentally, you get 115% of the stuff for 85% of the cost. This is why cities work so well. This is why they tend to grow. They're more efficient, and you get more stuff for less money. Who else does this, right? Well, ThoughtWorks, I mentioned, we scale by Dunbar's number. This country, we've got Manchester, London, Newcastle, not just one big head office. India, we've got 10 offices, I don't know. China, however many, right? We don't scale by having a giant office, we scale by trying to create smaller communities, smaller bits of smaller cultures that are decoupled. Spotify, you can argue the Spotify model is exactly an attempt to document how to grow a company using small world networks, using the squads loosely coupled from one another, with just enough hierarchy to enable cross-team, cross-organisation communication. Valve, the computer games publisher, they even, when they leaked their team, their handbook for new joiners, they had this in it. This was in plain sight 10 years ago. They said, we are scaling via small world network growth. This is what we do, because it's more effective. And then finally back to Amazon and AWS. They're growing in advance of exponential. They're growing with an exponent 1.15 in this graph. They get more revenue out than they should, as I said at the start. As they get bigger, it gets easier to get bigger. It's the same number as I was showing you for small world network growth in other situations. So for Amazon, right, as most companies get bigger, it gets harder to get bigger, and the reasons are mathematical. The reasons are to do with hierarchy, with age, with slowing down, with metabolism. The same reason that we slow down as we get older, the same reason that we're slower than a mouse and an elephant is slower than us. But as Amazon gets bigger, it's easier for them to get bigger. I'll refer you back to team topologies. Talked about team topology, software architecture, and flow. I'm using team structure, organizational structure, these network designs synonymously, essentially. As we put our teams together, we're building loosely coupled components around these streamlined teams, right? Decoupled, with enabling teams, enabling those teams to go faster. When you're building these teams around social networks, you're not limited by the structures imposed by hierarchy. You're limited only by the team that you have yourself that are isolated from others. And you can add more and more and more. So in summary, it's been, 2014, Martin Farrow and myself published the paper on microservices. And, I've been writing code, yes, but I've also been thinking about why those things seem to work. Why has it become so successful as an architectural style? Why is now data mesh exploding? Data mesh is an expression, I think, of microservices architecture. It's an expression of what I'm talking about as well. It's an evolution of microservices. And it's based around this idea of decentralization, decoupling, organized around stable concerns, business capabilities we called out, organized around your business domains, not technological concerns. Team topologies is a ubiquitous language we can use amongst ourselves to talk about how to structure ourselves to optimize for flow of information through small world networks. So I'll finally leave you with this. Social networks imply super exponential growth. Hierarchies, they slow things down. It's just maths. We can apply inversion of control for teams, and we can use forcing functions for flow. This is the research I've summarized. This is not my own work. This is a report back on what I've learned over the last decade or so. So team topologies accelerate scale, Quark and the Jaguar, and flow. And on that note, I think I'll say thank you very much. This really is the end. Thank you. And luckily, there's no time for questions. Ha ha ha. I'll be out there, though. Cheers.